All right, so now we're going to do an example of the voltage drop calculation that is in your code book. So if you can open up to the Appendix D, Table D3, we'll read the notes and we'll look at the example. I've copied the example that's in your code book on the whiteboard behind me. So the first note here, note 1 says, Table D3 is calculated for copper conductors sizes number 18 AWG to 4 odd. And for each size specified gives the appropriate approximate distance in meters to the center of distribution measured along the insulated conductor run for a 1% drop in voltage at a given current. With the conductor at a temperature of 60 degrees, inductive reactance has not been included because it is a function of conductor size and spacing. Note 2. The distances for a 3% or 5% voltage drop are 3 to 5 times those for a 1% voltage drop. So this table here, these numbers are for a 1% voltage drop. And the statement here in note 2 tells us that we just multiply that value by whatever times we need for a voltage drop. So 3%, we multiply the value in the table by 3. Note 3. Because the distances in table D3 are based on conductor resistances at 60 degrees C, these distances must be multiplied by the correction factors below according to the temperature rating of the conductor insulation used and the percentage load with respect to the allowable ampacity. Where the calculation and the allowable ampacity fall between two columns, the factor in the higher percentage column shall be used. So when you're doing a calculation and you load the conductor up to 53%, instead of being in the 50% column, you go to the 60% column. If the loading on the conductor is 65% of its allowable ampacity, you would go to the 70% column, etc. 4. For other nominal voltages, multiply the distances in meters by the other nominal voltage and divide by 120. So the table is based on a 1% voltage drop, so if we need 3, we multiply the number by 3. And if your circuit is 240 volts, instead of 120 volts, we'd multiply the number by 2. And if it was 347, etc. So you do the math in the equation. Note 5. Aluminum conductors have equivalent resistance per unit length to copper conductors that are smaller in area by 2 AWG sizes. Table D3 may be used for aluminum conductors because of this relationship. For example, for number 6 aluminum, use the distances listed for number 8 copper. In table D3, similar for 2 watt aluminum, use the distances for number 1 copper. 6. The distances and currents listed in table D3 follow a pattern. When the current for any conductor size is increased by a factor of 10, the corresponding distance decreases by a factor of 10. This relationship can be used when no value is shown in the table. In that case, look at a current 10 times larger. The distance at the center of distribution is then 10 times larger than the listed value. Note 7. For multi-conductor cables, ensure that the wire size obtained from this table is suitable for the ampacity from tables 2 or 4 and rule 4-004. Just a statement there. 8. For currents intermediate to listed values, use the next highest current value. What that means is, here, in this column, in the current column, say we had a load of 18 amps. So we don't have a listing for 18, we have 16 and 20. So what we would do, 18 falls in here, we'd use the 20 amps for our example calculation, all right? To achieve the number out of the table. Note 9 is the example. So students, you're going to get tested on this. We do it in years 1, 2, 3, 4, and you'll probably get it on the IB. All right? The example is in your code book. Take the time. I've got it written on the board here. We're going to run through it. All right? And pay attention because these should be easy marks for you. You have to be able to do this. As a journeyman, it's critical that we get the voltage drop rules down. So let's take a look at the example. It says here, from table 2, allowable ampacity of a 2-conductor insulated number 12 NMV 90 degrees rating is 30 amps. The given current, so the load current is 60 amps or 53% of the allowable ampacity of the conductor. So here they've done the math, 16 amp load current. Here's the 30 amp rating out of table 2 of the allowable ampacity. The distance correction factor used is to be from note 3, 85 to 90 degree conductor rating. We round up to the 60 degree column, and that is the 1.04. So on the example, we have the 6.1, the 3%, so the table is based on 1%. Our voltage drop in the circuit is going to be 3. We have a distance correction factor of 1.04 based on the loading. So out of table 2, 90 degree, number 12 is good for 30 amps. We do the math. 16 divided by 30, we've loaded it at 53%. We round up to the 60%. We go to the distance correction factor, and we come up with that number. So if we look here, up top, we got the 85 to 90 degree column. We've loaded to 60%. We come across, that's the 1.04. Where did we get this number? From the table. So there's our load current, 16 amps. We look up top here, you're looking at your code book at home. Here is the 16 amps. We come across number 12. We come down 16 amps, and we have the 6.1. So we have the 6.1 times 3 times 1.04 multiplied by the voltage of the circuit over what the table is based on, 120, which is 2. So we end up with 6.1 times 3 times 1.04 times 2, and the allowable length is 38 meters. All right? That's how you get to use the table. In the next video, we're going to do a practical example on the whiteboard where we know how far the load is, and we know where the overcurrent device is, and we're trying to figure out the smallest cable that we need. All right? All right, so in the next video, that's what we're going to run through. So thanks for watching.